Welcome all of you to the Joke Wrocław. I'm really glad that you all came here. Today our guest is Venkat, and we are really happy that you agreed to our invitation and you are here today with us. And to everyone who watched this on the stream, you can win JetBrains license. You just need to be the active on the YouTube chat. And if you will have the questions, I will interrupt Venkat and ask those questions. I hope you will enjoy that. And Venkat, stage is yours.
Thank you, Sebastian. I really appreciate it. Greetings to everyone at the user group there. I absolutely enjoyed my time visiting Wrocław in the past few years. It was great to be there in person to speak at the user group, but I'm as delighted to be speaking virtually here as well. Always a pleasure to interact with the group. So if you have any questions or comments, please post them along the way. And Sebastian has kindly agreed to ask those questions. You can ask the questions anytime you have it during the time, towards the end, anytime that's comfortable for you. I'll be delighted to hear your voice and hear what you have to say. So with that said, let's get started. We're going to talk about a dozen cool things that we can do with popular JVM languages. Well, one of the really beautiful things about JVM is JVM has a lot of different languages. You know, the rumor has it there are more than 200 languages on the JVM. But of course, from the popularity point of view, they really trickle down to a handful of languages. Of course, Java predominantly, there's no doubt about it. Java is probably one of the most popular languages in the world, leave alone just in the JVM. And of course, we also have Groovy and Scala and Clojure and JRuby, and of course, Kotlin as well. So what are the things we can do with these languages? But before I talk about these languages, I want to talk about why really talk about these languages and what is the significance of it. And the reason is we live in a polyglot world. You know, personally, I program in about 15 different languages. What I'm saying in those many words is I'm not good in any one of them. But I love programming languages. And one of the reasons I like to learn these languages is languages provide a set of tools that make us think very differently when it comes to programming. I'm not learning a language for syntax at all. In fact, that's the least interesting and the least important to me as well. But I look at languages because languages give me a way of thinking. Languages give me a way of expressing the ideas as well. And that's one of the reasons I'm really keen about programming languages. Well, the point though is because we are on the JVM, while we may predominantly write code in one language, we can, so to say, easily mix code written in other languages as well on the JVM. That's one reason we can benefit from these languages. Secondly, in the world of microservices, we may have different microservices written using different languages, so we can easily leverage the language that's right for the purpose, depending on the focus of the microservice. Now, I personally consider programming languages like they are vehicles. You know, I have a Jeep I really like a lot. I take airplanes to go to different cities. I got a bicycle I take to the neighborhood park. And these are different vehicles. Whether I want to use a bicycle or a Jeep or take an airplane depends on the distance I want to cover. Now, obviously, I don't think I want to take my car over to my park, which is literally next door. It's going to take a lot more time and effort to drive a car over there instead of just walking over or riding my bicycle. On the other hand, if I want to go to the neighboring town, I can't really take a bicycle because it's a little further away, but an airplane is also not possible. My car is the right tool. Of course, if I want to come and visit you, maybe when all this pandemic is over, you're not going to see me ride my bicycle all the way there. I got to fly, commercial airlines to get there. So languages are exactly like that to me. Depending on what I'm trying to do, I need to use different languages to get it done more efficiently. And that's one of the reasons why I really like these different languages. Well, from that point of view, I'm going to talk about a few things that have excited me about different things we can do in different languages. Let's start with accessing a file. Now, if you're writing code in Java, we know how painful it can become to read some of these things in the different ways to read files from the operating system or from the disk. Now, Java itself has evolved considerably over the past few years, and as a result, it's nice to know that a lot of these things we can do in Java as well. However, there is still inspiration from these languages we are gaining into Java. And, let's be honest about it. While Java is amazing, no doubt about it, Java is changing rapidly. Still, Java cannot possibly do everything that's possible in all of these other languages. That shouldn't really be the goal as well, because if the goal for Java was to do everything that everybody does, Java will lose its edge about what it's trying to do. So Java is evolving fast, no doubt, but Java is not going to do everything that every other language actually does. So in that sense, let's talk about how this can be used in different languages. So let's say I want to just read the current file itself quickly in this program. So I'm just going to start with a print line, and I'm going to say file dot, in this case, new file. This is Groovy I'm writing. And I'm going to say, in this case, I want to simply read sample.groovy. And then once I read it, I'm going to ask for the text from it and display the content of that particular text directly. Notice how trivial that was to be able to read the content of this file. So literally, I'm taking stuff out of the standard output from this and displaying it really easily. So it becomes easy to just read out of this and get the content out. So that's an example of how we can read files from Groovy, if you will. But what about Scala? Well, in the case of Scala, I can say scala.io.source and then from file, and I can specify the file I'm interested in. So in this case, I'll say sample.scala. But Scala's from file actually returns an iterator back to us. And because it's an iterator, I can use make string and I can combine the values into a string from the iterator. And there you have the file that's displaying the content itself very easily. So it becomes a really easy way to process it. Well, Kotlin also has a very similar capability, if you will. So java.io.file, and in this case, I can say a sample.kts. That's a file I'm interested in reading, if you will. And in this case, of course, I'm just reading the content of the file and I'm accessing it. Oh, you know what? They always say don't change stuff before a demo, right? So I was just spending the last about 5 minutes before this meeting, working on something else that I was, experimenting with, and I was switching between different versions of Kotlin, and I totally forgot about it. So pardon me about that. So I'm going to change the current to a different version here. So hopefully that helps me to get moving. So here back, I think I'm on my feet again. So let's run this and see what it tells us. So right there, I'm accessing the content of the file. So there you go. So I switched over to a more recent version of Kotlin that I was experimenting with. So right there, you can see the content. But I can say read a text right there and get the content out of that file as well. And again, here's a piece of code that's reading the file itself. So right there, you can see that content being provided to us. So that's an example of how easily you can read files without any ceremony. Now, obviously, in more recent versions of Java, you can also call read string, but it does require a little bit more effort than what you saw here, but not terribly bad, honestly. So again, we can use these kinds of low ceremony nicely. However, I haven't quite seen this one in a lot of languages other than Groovy. And that is to interact with the process. Now, let me explain what I wanted to do before I give you the example. I was working on an application where I wanted to, when a request comes in, I got to fire up a process, send a command to the process, execute the process, get the response back, and then display the result, do the processing of the response, and then display the result to the user. So this code, in all honesty, was not a large amount of code. It was about 150 lines of code. And I wrote it, and then I moved on, and I came back and looked at it a few months later. And when I looked at it a few months later, I was a little bit shocked. This 150 lines of code had about 75 lines of code just to talk to this external process. And I sat there thinking, my gosh, half the code is used just to talk to the process. What a waste. And I came across this feature in Groovy. So I rewrote the code in Groovy. And on that 75 lines of code literally shrunk to about 3 lines of code. Now, programmers will secretly tell you it's more fun to rewrite code than to reuse code, isn't it? So I rewrote the code in Groovy just to see how it is more concise, and I was absolutely happy. Well, let me give you an example here. Suppose I'm on the command prompt, let's say, and on the command prompt, let's say, all I want to do is simply use git help. Just to show you an example, git help. And when I type git help, as you can see, it displays the content of git help all the way to read about specific subcommand and our concept. Well, that's just git help. As a simple example, let's say I want to talk to Git from my program. So what can I do? Well, I'm going to create a string and I call it git help, and I'm going to just print it. So as you would expect, that's just a string, nothing really exciting. But then I go to that string, and this is one of the nice things about Groovy, is Groovy is built on top of both the JDK and the GDK. So JDK, of course, is the ubiquitous Java library. On top of the JDK, you have the GDK, the Groovy library sitting on top of it, which enhances the capabilities of the underlying Java classes. So the execute function literally returns a process object. So if you were on a Unix process versus a Windows process and so on, and I'm here on a Unix-like system. So as a result, you can see it gives me a Unix process. But then I can say dot text on it, and I can ask it to give me the text output. And I simply gleaned in on the standard output. As you can see, it says there are common Git commands used, and it pretty much is the Git helps output that I'm taking a look at right now, as you can see from running that code. Now, this is what I was talking about, where all that ceremony, all that noise, really to have to talk to a process simply goes away. I can fabricate my command as a mere string and call and execute on it and fire off a little text on it and have it executed. And that makes life really easy, as you can see, something to really think about how we can benefit from that. So those are some of the niceties we can look at. Again, along
there
the
is
way.
a question.
Oh, yes. I was just going to say, awesome. Go ahead, please. Yes.
About Groovy using Java, right? So there is a question that is there a limitation with Scala or Kotlin where Java libraries will not work with those language?
Really good question. Awesome. Thank you. Thank you for the question. So the short answer is no problem. The long answer is there is never no problem in programming, isn't it? So something will go wrong all the time. Let me answer that question in 2 parts. You mentioned Scala or Kotlin, and I want to split those answers apart if you don't mind. So Scala, let's take Scala first of all. Scala is a very powerful language, and I have the deepest respect for Scala. But Scala also goes off and does things on its own to really pack the power of the language. So there are 2 things I want to talk about when it comes to interoperating between the languages. Calling from Scala to Java and calling from Java to Scala. Now, calling from Scala to Java is relatively easy. There are a few rough edges, but for most part, it'll work just fine. So you can go from Scala to Java, mostly no problem. On the other hand, going from Java to Scala requires a little bit more effort than that, because there are some syntaxes that are easy and elegant in Scala, but when compiled to the bytecode, can look really hard to use from Java. So from the interoperability point of view, Scala to Java is relatively easy. Java to Scala takes a lot more effort. And so to answer your question, when interacting, when there are Java libraries and you want to call them from Scala, mostly you should not have any trouble at all. That should be relatively easy. When it comes to Kotlin, Kotlin to Java is really easy. Java to Kotlin is also relatively easy, much more easier than Java to Scala. The Java to Kotlin is pretty easy. Now, one of the few things is if your code is going to be predominantly used within Kotlin, you don't have to worry about things. But if your code is going to be used from Java, you may have to perform some annotations. You may have to annotate a few places and say, hey, I plan to use this from Java, so generate the proper exception handling throws, generate the proper code for static methods, and so on. Now, in both languages, I'll mention one thing. This is true for all languages. Now, when you have a language like Java, which came ahead of time, and you have languages like Scala and Kotlin, which came later, now, one of the things you may want to think about is what's going to happen if you have a keyword conflict. So, for example, let's say you're working on a project where you use Kotlin and Java at the same time, and your Java code has a function called when, W-H-E-N. And when you have a when as a function, well, Kotlin uses when as a keyword. So if your library contains a function named when in Java, your Kotlin code will choke up, because your Kotlin code cannot call the function when or a variable when, a field or property, if the name is called when. So what do? Here's the good news. You can easily use a little escape. So you can put a backtick, when backtick, and then you can call the methods. So you're telling the Kotlin compiler, hey, when you see the word when, it's not the when you know Kotlin, it's a when as Java uses it. So don't treat it as a Kotlin. So you can use an escape and you can go around. So the short answer to your question is there shouldn't be any problem as long as we work around these, these little glitches. You can use a backtick and do an escape, and you can work around. So for most part, you shouldn't have really that much trouble at all. It should be really cool to go through. So that's one of the things to really think about in terms of how these languages can be interoperated. So that's a good thought. I'm thankful for that question. Now, we talked about language features here. But one thing I'm going to talk about next is available in almost every language which has a lambda expression available. This is called the execute around method pattern. So to understand the execute around method pattern, let's talk about a class called resource. Now the class resource contains a constructor, and this constructor simply says output, let's say created. And then I'm going to say public, let's say in this case, let's call this as resource op1. And all it's doing is output op1, and then it's going to return the current object this. Let's create one more function really quickly here, which is called op2. And the op2 function simply prints out op2. But imagine that this function, this object is created, but it uses some external resources. Like, for example, external resources like a database connection, a file that's open, or maybe it contains a connection to a remote web service. Now we know one thing about garbage collector. So the good news about garbage collector is automatic. That's the good news, right? But it is not deterministic. So that is one of the negatives of garbage collector. It's automatic, but not deterministic. So you cannot tell when it would run. If your code has a lot of memory, the garbage collector may not kick in for a very long time. So if you create a resource right here, and then you say equal to new resource, and you call resource op1, and then you call resource op2, now the question is, what about the memory? Hey, you don't have to worry about the memory. If there's a lot of memory, who cares? If there's not enough memory, JVM will take care of cleaning it up. But what about external resources? A file that's open, a database connection, a connection to a web service. What do you do about it? Well, unfortunately, though, so what about external resources is the question. Now, unfortunately, we still have to worry about it. So in Java, what we have is a public void finalize method. And in here, you can say clean up external resources. So this is your database connection, your file, your remote web service connection, whatever. But unfortunately, though, if you run this code, what's going to happen? Well, to understand this, let's go over to the command prompt really quickly. But in the command prompt, I'm going to run Java 8 for just a minute. So Java C -d temp classes, and I'm going to compile the sample.java file right there. So now that I compiled it, Java -class path, let's go to the temp classes directory and run the sample. And notice it said created op1, op2, but it never called the finalize method. Why? Because there was a lot of memory. And so as a result, the garbage collector did not have a reason to really run after all. Now, if you ever want to rename the finalize method, a better name for this is called bad idea. So they should really never have created the finalize method. In fact, it is so bad, they finally recognized it and deprecated that method. Notice we got a deprecation error right there. I mean, just to illustrate the point, let's switch over to Java 14 right now. So now I'm on Java 14. I say Java C -d temp classes sample.java, and notice the deprecation warning you're going to get at this point. It says override deprecated API and use -excellent deprecation. So if I were to go back and compile this now with the -excellent deprecation, it tells me deprecation finalize and don't use it. Well, in my code base, in my continuous integration, I treat warnings as errors. And as a result, if anywhere in my code, my developers use finalize method or I use finalize method, we'll get an error because we don't allow finalize. So then the question is, what's the right way to solve it? Well, Java in Java 7 introduced a technique called ARM, which stands for Automatic Resource Management. So as part of ARM, Automatic Resource Management, you rename the finalize method as the close method. And then you implement right here. So you say implements auto closable. Now, auto closable simply says, run the block of code, the try block, and when you leave the block of code, go ahead and call the close method for me automatically. So notice now we can wrap these two in here. And the close is called automatically within a finally block. So we don't see the finally block, but the finally block is written for us automatically. So if you were to go back and run the code now, notice how it calls clean up external resource in the end automatically. Now, while this looks like a great idea, I'll be absolutely honest about it. I am not a fan of this at all. And the reason I'm not a fan of this is, if you look at it, if I forget to call the try, and if I simply place this right away, then we are back to square one. We are not going to have the close method call automatically. And I'm of a belief that if something has to be done, then we need to really design for it. And that approach was not a design at all. So I'm going to get rid of it. So how do I solve this problem? How do I make sure that this garbage collection of external resources happen for us automatically? Before I talk about it, let's step back and talk about something that helps us to understand what we are saying is not totally new. So go back to Java for a minute. Try, and you have some kind of a resource, and then you have some kind of a code right here. And then what happens? We know close is called automatically, right? So this is developed in the language. Java gave you that syntax and said, use it. Well, if you don't want that particular scenario, I'm sorry, I can't benefit from that. Here is another example we all know. Synchronized, and then you say synchronized what? Some object, right? And then you provide some code. But what's going to happen? You know lock is acquired acquired here automatically. So lock acquired automatically, or you wait for the lock. And once you get the lock, you execute the code. But what happens? Lock released automatically. You kind of see this pattern here, isn't it? That pattern is called the execute around method pattern. So the execute around method pattern is you execute that code, but around it, you acquired the resource and you closed it. And around it, you acquired the lock and you released it. But notice that is Java syntax. That is Java syntax. And you say, wait, I like this idea, but I want to do it for my own code. I don't want to use a try. I don't want to use a synchronize. How do I do this? So in other words, we want to generalize that execute around method pattern. So how do we do that? Well, here's an idea. First of all, if you write code like this, it's possible the user calls close, and we know this is wrong because we need a try and finally blocks, which is not happening. So notice what I'm going to do. I'm going to make the close method private. By making the close method private, line 23 fails compilation. And the programmer is like, darn it, I cannot call close, fine. But of course, this code is not a good code. It is not doing the right things. I'm going to go to the resource right there. And what am I going to do in the resource? I am going to change this to, the phrase over here is private, right? So I'm going to change it to private. And as a result, I'm going to say private resource. So by changing it to private resource, what I'm going to see is I cannot call line 20 after all. Why? Because line 20 is calling the constructor, which obviously is private. So as a result, I cannot call that from here. Now, what do I do? What's a solution? Well, let's really handcraft the execute around method pattern. So import java.util.function.consumer. So let's start with a little first step. I'm going to write for myself a public static void use, which takes a consumer of resource. We'll call it as a block. Then within here, I'm going to say resource is equal to new resource. I write my try with finally block. And in the finally block, I call the close method. Now remember, because we are within our own method of our class, we can access the private constructor. We can also access the private close method as well. Now within this, I'm going to say block.accept and pass the resource to it. Now, what is the benefit of writing this code? That right there is your execute around method pattern. So notice I go back to this code and say resource.use, and this gives me a resource on my hand. And I take that resource and then I say, thanks for giving that to me, resource.op1, and then I call op2, and then I complete that block of code. But when I run the code this time, notice how it created the object, ran over op1 and op2 in the block, and it automatically ran the close method in the end. So in other words, you are running those two pieces of code. In other words, that block of code you are running, and that block of code, which is the lambda, is executed, but around that block of code, you got a pre-op and a post-op. So this becomes your execute around method pattern. Some languages like Scala call this one as with another name. They call this often as the loan pattern. So as in, you get a rental car on loan, they clean up the car before they give it to you, you drive around the town, and then when you return it, they check for damages and then take it back in. So that's why Scala calls this as a loan pattern. So it's as if this object is on loan to us, and then we use it, and then we return back, and then they do some operations with it. A very powerful pattern. I showed this in Java right now using Java 8, lambdas obviously, but you can do this in almost any language with lambda expressions because it's a very powerful way of saying, here's a piece of code, but I want to do something before, then execute your code and come back and run something after. You can standardize the before and after and allow the right in the middle part to be executed differently. So it's a very powerful pattern. It's one of my most favorite patterns in reality because it nicely shows the power of lambdas and how we can leverage that to implement various policies. I'll give you an example where we used it. In a company I was working for, we had transactions and we had code we have to run within transaction. But at the end of that, depending on how things went, we have to roll back the transaction and log or commit it. And I noticed people were duplicating the code everywhere. So quickly what we did is we created a transaction.runWithin. And then, of course, that run within creates a transaction, gives us an object, a context object. Our code simply runs and updates the context and done. And then the run within transaction then picks up and says, if there was a failure, we'll log and roll back. Otherwise, we'll commit. So we were able to streamline this operation nicely so we don't have to duplicate that code, and we effectively use the execute around method pattern for that purpose. So that's one of my favorite patterns in different languages, and I've exploited that quite often in different languages as well. So we talked about 3 different things we can do with 4 different languages over here. Now, one of the things I really like in Scala is this concept of traits. So what are really traits? Traits are really interfaces to begin with. However, traits are a lot more than interfaces. So let's understand what traits do, first of all. So first of all, you could say traits are interfaces with method implementations. Now, you may look at this and say, come on, Venkat. You have Java with default methods, so what's the big deal? Now, this is what I love about traits in Scala. So Java interfaces are nice, but they are not stackable. And stackability is a very important characteristic. On the other hand, Scala traits are stackable. So what do we mean by stackability? So stackability is where you can take an object, and the object can use a trait 1, if you will, but then you can stack on top of it yet another trait 2. And you can stack a trait 3 and a trait 4. So when you make a function call, the function call will be intercepted by trait 4. And it can do some work and forward it to trait 3, and which can forward it to trait 2, which can then forward it to trait 1, and which can then forward it to the object. So you can have this nice chaining. So what does this really provide in reality? Traits in Scala are really compile time mixins. So this is one of the coolest things about Scala is Scala's traits are compile time mixins. And one of the cool things about mixins is mixins are stackable and thus are different from, very widely different from using the concept of multiple interface inheritance. So yes, you can have multiple interface inheritance in Java, but you don't have stackability in Java. I am not aware of any effort to bring in stackability to Java. So this goes to, thinking about like, gosh, Java is changing so much. Should I care? And there are reasons to still care because, as you can see, some features are not available in Java and probably won't be available in Java for a long time. So what does stackability provide in that regard? So to understand this, let's take a quick look at an example to illustrate how this works. So I create an abstract class called writer. And the writer abstract class, it contains an abstract function. We'll call this as write, which takes a text, which is a string. That's all it contains right now. Now I create a class called string writer. Similarly, you can have a file writer, a socket writer, who cares, right? You can have as many writers as you would like to. So extends from the writer. So as a result, I'm going to go ahead and say a val, we'll call it as target, is equal to new string builder. So I create a string builder right now, and then I say diff override. So override the write function. It takes a text, which is a string. And what am I going to do here? Target dot append, and I'm going to append the text given. That's all I'm going to start with as a first starting point. So we have a write function. Now, abstract modifier can only be used in a class. Line number 2 is not too happy with me. Let me just go ahead and abstract. So let me try that without the word abstract right there. I want to really make that function as an abstract method. That's what I want to do. And the return type is a unit after all. That's what we are trying to really provide in this case. Okay, so we have a function that we have created. Now what do I want to do? I want to write a function over here, so called write stuff, and it's going to take a writer. And the writer is going to be a writer object. And what I'm going to do here is the following. I'm going to say writer.write, and I'm going to simply write this is stupid, right? Very intelligent words right there. I'm going to just print out writer.toString. So I'm just going to ask for the writer's content. I'm going to print it. Now, what does the toString method give me after all? Well, override, let's say define toString, and that simply is going to return target.toString. So very simple, as you can see, something that's going to return back what we give to it. Again, nothing really exciting yet, but how do we use this? So write stuff, and I'm going to pass to it a new string writer. So the string writer, I'm going to ask it to write the words "this is stupid" into it, and you can see it printed. However, notice I'm not going to change any code about this line unless I've made a mistake. I'm not going to make any changes about this code, but I'm going to create a trait. But the trait I'm going to create is called an uppercase. So we'll call it as uppercase filter. And this extends from the writer. So notice it's a trait, and the trait says, I'm going to extend the writer given to me. So what do? Override def write takes a text, but it's a string. But then I'm overriding all right. But remember the chain I talked about earlier. So you have an object, but then you have a trait 1, and then you have a trait 2. Now, what we are doing here is you execute this function on this trait, but you want to call the function on the one left in the chain. So for that reason, you're going to put the word abstract override, which is kind of weird if you think about it. But you are saying, hey, I'm overriding it, but I'm not the terminal function. I am myself an intermediate for something else that can specialize even further. It's just funny, right? So you're here, you're saying, I specialize this function, but this one specializes me further. So I override, and I'm still abstract. So I'm overriding something, but I'm also being general enough for something else to further override. So that's an abstract override for that reason. And equal to, what am I going to do? I'm going to say super.write. This super is the one that's going to specialize. That's the trait on my left. On the other hand, write, take the text to uppercase, and you can convert it to uppercase and call the text right now. So what is the benefit of doing something like this? Well, the benefit is, notice now what I'm going to do. I'm going to call the write stuff one more time, but here I say with uppercase filter. So I'm combining the trait, as you can see in this case. So as a result, you can take this and communicate further through this, as you can see. So as a result, you can move this forward to from one to the next, as you can see, and you can see it converted to uppercase. On the same note, notice I can take this one right here, and I can say to And in this case, of course, rather than being uppercase, I'm going to change it to a lowercase. And this becomes a 2 lowercase, as you can see. And what's the benefit of that? I can take this and convert the whole thing to a lowercase as well. So yeah, okay, so far so good. But you say, well, what about mixing of these traits? The stackability would be really nice, isn't it? Well, let's give it a try again. I'm going to create a trait another time, but I will call this as a profanity filter. Now, obviously, is the word stupid a profanity? Well, it depends on whom you ask. My children, when they were small, would be very angry if I use the word stupid, because my wife told my children, you don't use the word stupid, that's a bad word. So I come along, I hang out with developers all day long, and I come along and I say, hey, that's stupid. And my children are like, oh my gosh, daddy is using a filthy word. Well, okay, so we want to remove the word stupid. So what are we going to do? We're going to take the text and say, replace all. The word stupid, we'll replace it with STUIPD. So we write a profanity filter right there. But what is the benefit of doing something like this? Well, notice I can take this and say with profanity filter, and as you would expect, it strips out the word stupid, but I can also do the following. Write stuff new string writer with uppercase filter with profanity filter. So notice how I am able to combine them together in here. So by doing so, we are telling we want to apply a stack of the functions together. So as a result, you can see it stripped out the word stupid, but it also puts them in uppercase. And just to illustrate the sequence of operation, if I go back over here and remove this and say profanity filter with uppercase, clearly we only look for lowercase stupid. So as a result, it did not remove. So that shows the order in which it ripples through. So in here, we had the profanity filter in the right, far right, then the uppercase, and then the string writer. So that's the sequence, and that's a stackability I talked about. I don't know of an easy way to do this in Java. Now, clearly, you can do a lot of code to make this work in Java, and I would even argue that a lot of code in Java 8 is still less compared to previous versions of Java. But those things are not naturally built into the language in Java. Whereas here in Scala, we can nicely benefit from this with the traits, as you can see, which is pretty darn good.
There's a question about traits. What if exception will be thrown by during any trait what is not terminating? By the way, traits look like decorator pattern implemented in language.
Yeah, what's the name of the pattern?
Decorator pattern.
Oh yes. So that's exactly what I was referring to. It's a decorator or a chain of responsibility, but you are absolutely correct. It's more like the decorator. So when I use the same example in Java, that's exactly what I do. When I use it in Java, I often show this using the compose method of functions and use it as a decorator. So you nailed it. So this is actually the decorator pattern implemented in the Java. So the stackability in Scala. So stackability in Scala is really a great example of the decorator pattern. You're absolutely correct. You nailed it. What about exceptions? Well, exceptions are always a sticky idea, isn't it? So for example, if I go back to this code right here, and for whatever reason, let's say for a minute you call this function, and rather than returning that, if I were to say, throw new runtime exception in here, and if I say exception and oops, well, this is still a sequential code, right? It's not a concurrent code or anything. In this case, I get an incompatible type override, abstract override. Let's see why it's complaining to me. It's expecting a unit, but it was it gave a unit, but it was a nothing. So again, we could do something like, for example, we could come in and say, if it's a particular string, then throw an exception. We could do something like that. Maybe I can try that. But the point is, it's still a sequential code. It's not non-deterministic. It's pretty non-deterministic. So what you could do is you could say, if text is equal to, blah, I could say throw, a new runtime exception and something like that. You could try that. But if you throw an exception, what's going to happen? It's going to blow up on the call stack. So think about this as what's going to happen to exception when you have polymorphism, like you call a base class and a base class and a base class. How is exception going to be handled? Same scenario, no difference at all. So essentially, this is not going to be any different than a normal execution. So in this case, you can pretty much say, whatever you send me, I'm going to blow up. So I'm going to just change it to a true to see if it's happy with me to do that. And then we can see the exception thrown up at that point. Yeah, so right there, it simply says runtime exception and gives you the call stack. So exception is not a problem when it comes to trades, unlike your stream-based API, which can really mess you up. So exceptions are not a problem. It's still a sequential code. It's still a deterministic code. And so think of this as exception handling when you do polymorphism. You have a class, a base class, a base class, a base class. What are you going to do when you have exceptions? The same stack trace, same concepts apply in this case also. So I'm going to just yield to see if there are any other questions before I move on to the next one. Now would be a good time to answer a few more questions if you have any.
Yes, there is a question more accurate about Indian software market, but I think we could do this more general. Which language use for start as a developer for Android purpose, for example?
Yeah, so explicitly for Android, you have a couple of different choices, obviously. So again, where in the world you live shouldn't matter at all for making those decisions because it's a technology, right? Why would it be different in India versus Afghanistan, for example? But the point really is technology-wise, you have Java or Kotlin. Now, 75% of programmers, from what I know, who are programming Android are using Kotlin. I'm a technologist. I like code. I like to talk about programming. I stay away from as much as I can about non-technical things like politics of companies, lawsuits between companies. I don't have any desire for those things. So I'm going to skip that part and say, because of legal and because of a lot of things that are happening, there's a preference for Kotlin more than Java when it comes to Android, because you have multiple companies involved in it. But on the other hand, Google has invested a lot of time and effort and resources and money and people into Kotlin itself, and they are very supportive of JetBrains in their effort to continue to develop Kotlin. So Kotlin plays a very strong role for Android development when it comes to developing application for Android. So 75% of the people are using Kotlin, so there is no surprise related to that. I hope that answers the question. If not, fire back with more details and responses, and we can discuss that even further. Okay, so with that said, let's talk about one other thing. And again, this can be done in a lot of other languages, but I want to show you how beautifully this shines in Java so we can look at this. So let's go to Java for a second. So let's say for a minute we have names given to us, and names is equal to list of, and I'm going to say some names over here. So given these sum names, the problem given to us is a print comma separated the names in uppercase of length, let's say 05. So how do we really do this? Now, if you really think about it, doing this in imperative style of programming is really easy. Well, that's what we think, isn't it? So we start with the traditional for loop. Int I equal to 0, I less than, names dot, is it length, is it size, is it count? And you say, Venkat, come on, that's not done since Java 5. There's a better way. So string name coming from names. Oh, of course, if name dot length is equal to 5, then what do we do? Yeah, that's a value of 5. Then we can say print line, and we can simply say name dot to uppercase, and you can print that name in uppercase. That was very easy. You say, wait, but the requirement says names of length 5, comma separated. Oh yeah, sorry, we forgot that. There you go, you have comma separated. And then you say, oh, Venkat, come on, they really meant on the same line. We'll put them on the same line, not a problem. But then what do you notice? You notice a stupid comma in the very end. Have you noticed that in your own code? We all have, isn't it? But the more important question is, how did you feel when that happened? You were in denial. You said, that couldn't be happening to me. What a nonsense. And now you're thinking, how do I get rid of that comma? And then you say, hey, I can create the string. I can strip out the comma in the end. And then you're like, darn it, string is immutable. Now I got to make a copy of the stupid thing. Or you're thinking, maybe there's a way to fix it. And then you say, gosh, I can use a string builder. And your colleague is like, string builder or string buffer? And now we're like having a 20-minute discussion as to string builder or string buffer. It doesn't really matter, right? But that's not the problem we want to solve. So you can think of like, that's not really helping. What can we do? And then your colleague says, come on, there's an easy way to do it. Really? What is it? Well, all you have to do is not include the comma if it's the last element. Oh my goodness, how did we not realize it? But how do you know it's the last element? Oh, to know it's the last element, simply start I equal to 0. And you're like, oh my goodness. 30 minutes later, we are still struggling with it. In the meantime, the boss comes around and says, are you done yet? And this is really vexing. Well, simple things have to be really simple, isn't it? So this is where we can use a nice way to combine strings, and that comes from the collectors library in the case of Java 8. So what we can do is output, but then we can say names.stream, where streams are really an internal iterator. So you have a name.streams, which is an internal iterator. And then what you do here is you say a filter given a name.length is equal to 5. Well, then you perform a transformation, string to uppercase and get me the uppercase for those strings. Then you say dot collect. But then you say, I want to collect it by joining using a comma without any effort at all. So you can see how really easy that became to concatenate those with a comma. So in other words, you can concatenate with anything you want to concatenate with, and it is smart enough to know only to combine objects with it, but not put a comma in the very end. So that is, again, you can do this in Java, Scala, Groovy, Kotlin, almost all these languages have some kind of ways to easily do this, and you can combine things very nicely, and it removes the ceremony. So that is something we can do effectively to bring that in. Now, looking at this though, we can go a step further and think about program efficiency. Now, in Java, you can do something like this, but not so easily as in Kotlin and Scala. So to understand this, let's take a look at an example. Let's say we have a compute function. And the compute function, let's assume, is going to take some time. We'll say time consuming. And then I'm going to return n times 2. Really trivial, but that's a good start. Then I say x equal to 4. If I say x is greater than 5 and the compute of x is greater than 7, I'm going to say over here a print line of path 1. Otherwise, I say print line, in this case, we'll say a path 2. So that is a Scala code, as you can see. Well, here in Kotlin, I'm going to change it to a fun. I'm going to change it to a return. I'm going to say the return type of this is an integer. And so I went from the a code which is using the Scala syntax to Kotlin syntax. Other than that, I've kept it pretty much the same. When I run this code in Scala, you can see that in this particular case, it did not run the compute function. What about Kotlin? In the case of Kotlin also, it doesn't run that function after all. And the reason for that is, we know it's called short circuiting. So because of short circuiting, it did not run that code at all in this particular case. Well, good news. But what if you really wanted to do the following? If you wanted to say a temp, and then you said val temp is equal to compute. Similarly, in the case of Kotlin, if you were to say a temp is equal to compute x and change this to a temp, Well, now when you go back to Scala right here, Scala says, I will execute compute, then take the path to. What a waste, isn't it? Now, clearly the question is, why did Scala not avoid calling the compute function? Now, in this example, as you can see, we'll call a word check. And notice compute was called before the check was called. And it says run the code, then check. Similarly, in the case of Kotlin, we can see that it runs the code and then it comes to the checkpoint where it's checking if the value x is greater than 5. So again, run the code, then call the function, which is the do the check. Now, this is a waste of resource, waste of time. But why did Scala not smartly avoid this call? The short answer is side effect. Scala says if your function compute has a side effect, it's making a database connection, it's putting something to a database, or logging, writing to a file, what have you, then I should run it. And if I don't run it, it might be an error. Now, it's purely a side effect. Now, you may ask me, aha, Venkat, you say Scala runs that because of side effect, but a minute ago, you called a compute from here. And Scala chose not to run. And even there was a side effect. Why did Scala not run there? It really comes to two words: language specification. What do the two words language specification mean? It means the following in English: don't argue with the language. That's it. So languages can make up stuff and they will follow that. You can't question it. Languages say, even if a function were to have a side effect, we may not call it in a short circuit scenario. On the other hand, when the function is called in a non-short circuit scenario, the language specification says we will call it. And you're like, okay, I get it, but I don't like it. So what can I do? You can come to Scala and say lazy. So by marking it lazy, you are telling Scala, don't bother calling it. Notice it did check and path too. That's it. However, if you change it to 14, notice where the compute is called: after the check and not before. So it did not call the function right there. It waited until you access the temp, and then and only then it ran the compute function. So as a result, you can see that it delays that execution lazily. Same thing in Kotlin, just a different syntax. So by lazy, now this syntax is actually much deeper in the case of Kotlin. It is using a concept of delegation, and lazy is an example of delegation in the case of Kotlin. So when I run the code right here, what you see in the output is a call to the compute function, but the call happens only after the check and not before, and only if it really is needed. So again, if I go back and run this code, what you're going to see here is the call to check first, then it's going to call compute, and then it's going to go do the path and print out, as you can see in this particular case. And so that's a delayed evaluation. So lazy is a key word in the case of Scala. Lazy is not a keyword in Kotlin. Lazy is a function in the case of Kotlin, implemented as a delegate. And that's basically what you're seeing here, is in terms of what is built into the language itself. So that's basically how the language deals with it really nicely in terms of its capabilities. Yes, please.
Yes, there is a question. Could you explain how stream internally iterate elements?
Yeah. So when it comes to this is, I'm assuming, for Java. So if I were
yes, exactly.
Thank you. So if I were to take, let's say, numbers, let's say numbers is equal to, and I'm going to say, let's say a list of, let's take these numbers over here. Now I say numbers.stream dot function, filter, and I'm going to say, given an element mod 2 is equal to 0. And then I'm going to say dot, let's say map, given an element times 2. Then I say dot map, given an element, let's say element plus one, just as a silly example, right? So then I say for each system dot, let's say system dot out, and then I'm going to say print line and print it. Now, when you look at this code, this is a functional pipeline that we are seeing in front of us. Now, what is this going to do? It is going to take these values and go through this filtering and provide the data. So list of numbers 1 to 10, when you run it, you can see a few more values out there. Now, how does this actually work? Now, what streams actually do is, let's step back for a second to understand this, if you don't mind. So if I go back and say output right here, and I'm going to just stop over here and provide a close of that. Now, this code will not compile, obviously, because for each is not a function that returns anything. It's a void function. You could have printed this in Kotlin, but not in Java. So let's ignore that for a minute. But I want you to quickly note what you're getting. Notice the stream reference pipeline. Just keep that in mind with the F1 ending. Now I comment that out and I run the code again. Notice that's a pipeline. Now comment that out and run this. Notice the pipeline. So what does this really mean? I want you to think about this a little differently. So if I were to say over here, import, let's say java.util.stream.star. Now I'm going to say over here, throw that away. I'm going to say stream, stream of, let's say, integer, and I'm going to say s1 is equal to, and that number. Then I'm going to say, let's say stream of integer s2 is equal to, and I'm going to say this is s1 dot filter given an element mark 2 is equal to 0. Don't write code like this, but just an example. And then, of course, if you say s3 is equal to s2 dot map given an element e element times 2, and one more before we are done. So this is going to be s4 is equal to s3 dot map given an element plus 1. Now, if I output right here, so output s1, that's a stream as we know. But if I output s2 and I output s3 and s4, they all are really streams. So, but notice they're all different objects of streams. So what's really happening is the question. What's really happening is the following. So if you were to think about it, if I say function dot function like that, now when you look at this, go back to what we saw earlier. So if you were to go to this stream API, and if you were to just go through this pipeline, so get rid of all of these semicolons and get rid of all of these guys. So we have a functional pipeline with us again. But when you look at the functional pipeline, what happens? It is taking these and literally this is what it's doing. This is the filter one function. This is the map function. And this is the map function. You and I see this as three functions. But what they do is they take the filter and they combine it with the map and they create one function. Then they take that and combine with the map and they create the second function. So this now is one function, not three functions. So here's a way to think about it a little differently. If you want to think about it a little differently, how it's combined, this is called fusing. So in other words, the intermediate functions, are fused and only terminal functions like for each run those on demand. So in other words, here's what they actually do. So if you think about it a little differently, you can do the following, right? Function integer comma integer f1 is equal to given an element times 2. Now you can create a function integer comma integer f2 is equal to given e plus 1. So think of this as your map and filter functions you provided, right? So now you can do the following. You can output, well, actually, let's do it this way. You can say over here, a public static void, let's say print. It takes a function, integer comma integer, func, and notice what I'll do here. I will simply say output func.apply, let's say a 7. So if I take the print and call the function f1, We know 7 times 2 is 14, so the result better be 14. But you can call the print f2. We know 7 plus 1 is 8, so the result is 8. But notice function integer comma integer, f1 and then f2. That's the fusing I was talking about. So we took the function f1, we also took the function f2, and then we said fuse it. And now we got one function instead of two functions. And what does this function do in that case? Well, now you can see that I can call print right here and pass this function. Pardon me. What is this function name? We'll call it f3 is equal to. So f3 is a combination of that we're going to pass here. So as a result, when I run the code, 7 times 2 is 14 plus 1 is 15, and the result is 15. So you can see how these are fused together. This is exactly what's happening under the hood, logically speaking, in terms of what streams do. Streams also use what are called splitterators, but a splitterator normally is for parallelization. So there are two concepts here. One is the combination of functions. That's the one thing. The other is really how these functions are really split for parallel execution. And that's basically how these things are put together. It's a combination of fusing for the lazy evaluation and the combination of splitterators for parallel evaluation. I hope that answers your question as to how the streams actually do things internally by combination of fusing the functions together and by combination of splitterators to execute parallel. Fusing is for lazy evaluation. Splitteration is for parallel evaluations as well. And that's how they split the streams into pieces and execute it. So hopefully that gives you an idea about how that works. If it doesn't, fire back with a question. We can go into more details. Okay, so one of the things that Java is introducing, which is pretty cool, is pattern matching, which is also available in other languages like Kotlin and Scala. But I want to quickly show an example of this in Kotlin just to appreciate how beautiful this really is. So I call process with a 1. I call process with a 15. I call process with a string, let's say, hello. So in this case, if I create a process function, which takes an input of type any, but then I say when on the input, and I can then say else print line whatever. And if you really want, you can make this an expression as well. So you can simply return whatever. Well, in that case, I want to take these functions, as you can see in here, and I will simply ask it to print the result of these operations. So let's try this again. So I'm going to go back and say, this is print line, and I want to just print the result of it. But what am I really looking for in here as an input? Well, as an input, I got different data coming in. But in this case, what I'm going to do is that I'm going to say 1, and I'll simply return a 1. And then I'm going to say here, in the list, 13 to 19. And I'm going to go ahead and print out a teen. So you can see how it says 1 for 1, teen for teen, and then it says whatever for hello, right? That's what it's going to return for us. Now, in this example, a conditional branch, oh, we better be careful what we return. So this has got to be a teen, right? I started printing, unfortunately. That's an error, right? So that's basically, a string we need to be returning. Now, obviously, you can also do is a string, and then I can simply say got a string. So you can see how beautifully you can pattern match or match on the arguments and return different results, a very concise syntax. Now, you can do something similar to this in Java because, as you know, in recent versions of Java, switch is a expression, not just a function. So this is leading us towards a pattern matching syntax we can beautifully benefit from. But not only that, you can benefit from auto casting really nicely. So what is auto casting? So suppose you go back to this code and you say got a string, and then you say of length. And what is the length here? Well, you can simply say here input.length. That is amazing, isn't it? Why? Because you just went up to input and called a length function on it. Make no mistake, input, which is of type any, does not have a length. So if you try to do a input.length, you will get a compilation error because length is not a property of any. So as a result, that fails compilation. But the compiler is very smart to say, aha, here it's a string. In as an example in Java, right? So suppose in Java, I have a public static, let's say, void process, which takes an input of any object. And then here you ask the question, if input is an instance of integer, you could print out, right, got a number. So we can simply say, got a number. Oops, let's try this, got a number. On the other hand, you can say if input is an instance of string, what can you say here? You can say got a string. Well, now, if you were to call process after all, and to the process function you pass a 1, or you call the process and send hello, you will notice that in this particular case, you are calling the process function. Hey, this is Java code, so you didn't see that. So this is going to be object input right there. So you can see how you are able to call this function and pass that right there. So as a result, you got a string. But in the case of Java, if I say of length, and then if I say input dot length, right? Input dot length, what are you going to do? It's going to give us an error, isn't it? Why not? Why? Because input is of type object and it doesn't have a length. So what do we have to do? We have to write this beautiful code in Java in the previous versions, isn't it? So you have to say in Java string. Does anyone know what this feature is actually called? Well, that feature in the case of Java is called casting, isn't it? Again, I put this in the wrong place, as you can see. So I want to take this one, a number got a string of length. That's what I really meant. So let's go back to string of length. And if you notice over here, that's going to be an error because you cannot call length on input because object doesn't have it. But what is this feature called? You know this is called in Java as a casting. But I call this as punishment, right? So you're being punished in the case of Java. So what did Java do? I mean, would you hang around with somebody like this? You're sitting at a table with them and you ask them, did you go to the movie yesterday? I did. And then you ask them, how was it? And they say, how was what? And you kind of roll your eyes, right? Never mind. And you go to another table. Well, we don't talk to people like that. We converse in a logical, continuous flow. Hey, did you go to the movie yesterday? I did. How was it? Oh, it was absolutely terrific. I loved it. So we continue on the conversation. Whereas here, Java is like, I don't know what you're talking about. Well, dude, you just told me that input is a string. I did. What is the length of it? Length of what? Right? That's basically what we've been doing. Well, thankfully, we don't have to do that anymore. What we can instead do in Java is the following. You can take this and say stir, and then you can simply use that stir locally over here. So this is a smart casting as you see up here. So notice it says got a string of length 5 and gave you that value because that variable stir in the instance of nicely becomes a string type only within this block of code. Make no mistake, you don't have this outside of this. The scope is not available right outside. It doesn't have a clue what that stir really is at this point, so you cannot use it outside. So that stir is a smart casting of that input into a string only within that block of code in the case of Java. And this is going to become even more powerful in the future with pattern matching. So you will come very close to what you can do in the case of Kotlin. So that is one thing you can do nicely. Well, going a little further, we all have written code using XML at some point. Now, raise your hand if you love writing XML. I didn't see anyone raising the hand over here. Well, so that kind of proves the point, right? No, nobody likes XML. It is a disaster. It was never meant for human beings to ever deal with directly. And I have this theory: XML is cute when it's small, gets annoying when it becomes bigger. So the bigger the XML is, the annoying it is. But XML is kind of painful. But what if you really have to generate an XML document? So to understand this, let's take a little example. So I'm going to create a little example of languages. So I have defined languages like C++, written by Strewstrup, Java by Kotlin, Lisp by McCarthy, Ruby by March, so a bunch of languages. But I can define a builder is equal to new groovy.xml.markup_builder, and I'm creating a builder object here for us to use. Then I can say builder dot languages. So I'm going to ask it to say languages. Now, languages is an arbitrary name used on the markup builder. This is a beautiful example of the power of DSLs and meta programming at the same time. So when I call languages, the builder says, gosh, I don't know of anything called languages, so I'm going to assume you meant an XML root, and immediately a small XML baby just popped out, as you can see. So that's basically the languages that you see here. Within this, I say language. And now when I run it, it's a child of that. Well, we can go a little further. We can say langs.each. And within that each, we can say language right there and drop that in. Now we have 3 different languages or 4 different languages in this example. So we would expect to see 4 children being generated. But then you can go back here and say name colon and maybe the name of the language, which is the key. So you can specify a key comma value as a pair, and you can say, just give me the key alone. And you can say name is C++, name is Java, name is Lisp, and so on. And then as a child of that, you can say author value, and that can be a child element of that as well. So you can start creating XML documents very nicely with this kind of approach. So you can see the power of the language. Not only is this showing the benefit of using something like this very much here, but also our ability to create our own DSLs as well. That's one of the biggest benefits you get out of this, is nicely to bring that together and have that display the content depending on whatever you're trying to build. You can there are so many builders available in Groovy. You can use the XML builder. You can use a swing builder even to create a swing application in a similar way, or you can go off and create your own builders for your own domain as well. So a very, very beautiful, powerful concept, as you can see. Well, a couple of more things I want to quickly talk about. One of them is tail call optimization in the case of Scala. Now, Kotlin also has this feature, but the rumor has it might get removed. One of the problems is that in the case of languages, because the JVM doesn't support tail call optimization, this becomes a burden on the languages to do. But nevertheless, let's take a look at an example. Suppose we have a function like this. So let's say, oh, this is Scala. So define, let's say, factorial. And the factorial function takes a value n, and it's going to return a big integer, let's say. But what are we going to do within the factorial function? I'm going to say here, if n is less than 2, we want to simply return a 1. Else, I want to return a factorial of n minus 1, but n times the factorial of n minus 1. So that looks pretty innocent, isn't it? So we can call factorial of 1, if you will, and we know factorial of 1 is just a value of 1, and so we should really see that being a return, a big int after all. So let's try that with a big int. So we should return really a value of 1 after all in this case. But what about factorial of 5? Well, factorial of 5 is a 120, so we should really see 120, not a problem. Now imagine, remember the day you discovered recursion? You were blown away, isn't it? You were like, oh my gosh, this is amazing. You can solve a problem using a solution to the problem. I have to tell you, I remember the day I learned about recursion. I ran out on the street when it was raining and I celebrated because this is like, oh my gosh, this is amazing way of thinking. You can solve a problem using a solution to a subproblem. What a novel idea. But then you get excited and you're having this recursion party, right? And as you're having this recursion party, one of your people in the group who doesn't really get along with anybody comes to you and says, so you think recursion is cool, huh? And you're like, oh, recursion is awesome. And then they say, really, why don't you try that? And you run this with the 5,000. What's going to happen? It gave a result. Then they say, okay, try with 10,000, they say. And when you run it with 10,000, what happens to this code? It unfortunately, well, in this case, it's still holding up. You can go further with 50,000, whatever that limit is. I'm kind of curious now. But at some point, you're going to get a Stack Overflow exception, isn't it? There you go, Stack Overflow error. So the party is over. You're sitting alone and everybody is gone. Why? Because recursion looked awesome, but doesn't work with large values. So what can you do? Well, Clojure and Scala provide the facility to do tail call optimization. But what is tail call optimization? There is a phenomenal book out there called SCIP, which stands for Structure and Interpretation of Computer Programs, SICP rather. So Structure and Interpretation of Computer Programs, a beautiful book. They talk about two things, a process versus a procedure. So a procedure is the code we write. On the other hand, a process is the code. On the other hand, a process is the code that runs. So what does that really mean? You can write in terms of process, a procedure rather, and in terms of procedure versus a process. You can write an iterative procedure and it can run as an iterative process. Or you can write a recursive procedure, and when you run the code, it can run as a recursive process. So this is what we did here. We wrote a recursive procedure, and it ran as a recursive process. But what if we can change this to, you write a recursive procedure, but it runs as a iterative process. So the compiler is smart enough to convert your recursion into a loop behind the scenes. Then we can use recursion without the Stack Overflow problem. So this is where the tail call optimization really comes in. But the tail call is where, look at this code for a second. What is the last operation we perform? The last operation is the multiply. So this code has to wait for the factorial to return before it can do the multiply. Let's try this a little differently. It failed at 50,000, remember that. So I'm going to take this 5 again. And for the 5, the result is a 120 as we know, but I'm going to rewrite this. So I'm going to say factorial of n, comma, and I'm going to say result, which is a big integer, is equal to a 1. So I'm giving a default value for the result in this particular case. Then I say if the number is less than 2, return the result. Otherwise, what am I going to do? Otherwise, go ahead and call the factorial for me, please, but then pass n minus 1 comma result times n. So I reworked the example just a little bit. So in a sense, what we did is we converted the function from a recursion. So we went from a recursion to a tail call a recursion, right? So tail call, a tail recursion, that's what it really is. We went from a recursion to a tail recursion. So what's a tail recursion? Tail recursion is where the last command in a function is the function itself. Notice how it performed the multiply first, and then it called the factorial in the very end. So the compiler will now, so compiler can then convert this tail recursion into a iteration under the hood. So I won't have time here for this, but I would, if you're so curious about it, write this code as a regular recursion, compile using Scala C, then use the tool Java P and look at the bytecode. Then write it as a tail recursion, compile with Scala C, and use Java P and look at the bytecode. You'll see the bytecode on the, when you use a recursion is recursive. When you use a tail recursion, it simply becomes a iteration. So as a result of this, what's the benefit we derive out of this approach? The benefit we derive out of this approach is I take 50,000 right there and execute the code. Remember that one failed the last time. It failed because of Stack Overflow exception. Notice this time it did not fail. No, don't try to memorize that output. That's a very large data, but that's a tail call optimization. So again, there are some restrictions and limitations to it, but illustrates the benefit of using a tail call optimization really nicely. Well, that brings us to two more things I want to cover together, which is using extension functions in Kotlin and how we can leverage fluency out of that. Well, first of all, Kotlin is a language without really much of ceremony. You don't need semicolons. You don't need to write classes. You don't need to write main if you don't want to. So there's a lot of nice things that Kotlin offers. And also in Kotlin, you can use infix notation and remove the parenthesis and the dot as well. But in that regard, you can write what are called extension functions. So for example, let's say greet is equal to hello. So if I print out greet right there, you can see the greet is simply printing hello. But imagine if you are meeting a very good friend after a long time, especially after this pandemic, you're not going to go to your friend and say, hello, right? You're going to scream out of your lungs and you're going to greet this function. You want to shout out at this particular friend of yours. But shout is not a function in the language. I think we should have a function called shout, isn't it? But how sad there's no shout function. Well, you don't have to take no for an answer. What you can do is you can say fun string.shout is a function is equal to, and you can simply say to uppercase, and you can implement it like the way you really want to implement. So when I run the code this time, you can see that we are able to introduce a function, which is the shout function. So these are called function extensions in the case of Kotlin. So extension functions, they call it extension functions more than extension methods, but these are extension functions in the case of Kotlin. So you can introduce extension functions very nicely, as you can see. So what is the benefit? The benefit is you can introduce domain-specific functions to your code, and as a result, you can introduce things that would make sense based on your domain, even into third-party classes. Clearly, I didn't define the string class, but I'm able to add methods to it here, as you can see. Likewise, the fluency in Kotlin can be exploited. Imagine you can bring your own functions, but you can also have fluency with them. So to illustrate the fluency, I'll give you one example here. So suppose you wrote for I in 1 until, let's say, until 5. And I'm going to go ahead and print out that value of I. So you can see that in this case, the code is, yeah, it's okay. We used to kind of clutter and noise, in general. But when you look at this code, what does it really provide over here? Oh, come on. Let's see if I can type into that. My ID editor is kind of misbehaving right now. Hey, hello. Shall we work? Please change. So there we go. Let me try this again. So right there. So in this case, when I run the code, yeah, it's a little smelly, right? I'm not too happy with it because it looks a bit noisy. But here comes the charm. When it comes to your code, Kotlin has what are called infix functions. So in other words, you can take any function, fun, let's say foo, which takes an integer int, right? It does whatever it wants to. You can take that function, but you can define it as a infix function. Now, in the case of until is already an infix function. So notice what I can do here. Rather than writing the code like that, what I can do is simply come up here and say 1 and until, and I can remove the dot and the parenthesis, and I can run the code like that as well. And when I do, you can see how it still produces the same result, but I don't have to have the ceremony of the dot and the parenthesis. So as a result, you can write code that is absolutely clear. So class car, for example, let's say year integer, and I'm going to say car equal to car 2020, but I'm going to say car dot drive 10, whatever that distance is. So you can say fun drive, hey, that's a fun drive. And I can say distance is going to be an integer. And I can specify here print line you called. So you can see that in this case, we call the drive function on the car object. Nothing wrong with writing code like that. In fact, if you really wanted to, you could, drive called with, let's go ahead and say put the distance to make the compiler happy. But on the other hand, while you can write the code like this, you can make it as ceremonious as you like to. Nobody can stop us from doing that, isn't it? Let's put the year as well. It's just complaining to me. That's again a beauty of the compiler telling us we got stuff that we are not really using. Well, okay, but while you can write the code like that with a lot of noise and a lot of ceremony that you may otherwise have, you know what? I'm going to just get rid of this for a second. So we don't need the year after all. So why bring it in? So we all love ceremony, isn't it? Noise. So that's our car object that we created. So I'm just calling the function drive. And you called with the distance, whatever the distance value is, I want to go ahead and print it out. Well, given this, of course, in this particular example, I'm going to say, why not simply say car drive 10 like that, huh? Well, the compiler says, really nice, gives a nice clue and says, hey, you may really want to use a infix function. So I go ahead and mark it as infix for our own code. And you can see how we can remove that ceremony and we can use it right here. And of course, in this case, if you really want to bring the year, you certainly can. Just need to make it a property. So val year, which is an integer. And then, of course, this becomes a year, as you can see, so that we can use as well. So the point really is that you can basically have these infix functions to reduce the ceremony in the code and makes life a lot easier and pleasant to work. And that's, again, Kotlin. So Kotlin is a great language for creating DSLs, domain-specific languages, because of not only lack of ceremony, but ability to do extension functions and the ability to really, remove a lot of clutter in the code as well. Well, if you're interested in looking at these examples, you can download them from my website. The URL is given there. I'm not in a rush to run away, so I'll be glad to stay behind and answer questions. Any questions, any comments are absolutely welcome. I hope that was useful. I really want to thank you for taking the time to join today, and I'm open for any questions or comments that you may have. Thank you.
Yes, there is one question. In the Java example, when you show us smart casting, which version of the JDK did you use?
Yeah, so this one is Java, let's see, minus version. I was using version 14, that's what I was using. So I believe the smart casting is available in 14, yes.
Yes, there is no further questions. So everything what I can say, so it's thank you for coming here to the Juk Wrocław, but it's for everyone worldwide, Juk now. I hope that someday when everything will end, this pandemic, you will come to the Wrocław and we will just sit together and talk about new extra features of Java, just personally.
I would love to. Anytime you let me know, I'll be there. Absolutely. Thank you so much for having me there. I really appreciate it. Thanks everyone for attending.
Thank you. So thank you everyone for coming and goodbye.
Thank you.